Welcome to lecture series on advanced linear algebra. In my last class, we have seen to answer the question that whether a system Ax equal to y has solution or not. The meaning of these questions we have seen in terms of linear combination of vectors for n less than or equal to 3. I mean to say over the xy plane or over the Euclidean space, we have seen that solution of the linear system of equations is equivalent to the questions whether is there possible linear combination of the column vectors of your matrix A, which will give me right hand side vector, please. This we have seen for n less than or equal to 3, please. The question is it possible to generalize the same concept? Since up to n equal to 3 we can visualize 3-dimensional space, but as you cross n greater than 3, one cannot visualize this picture of the vector concept there. So, we need to extend this concept more algebraically, and for that is why I will introduce a new concept of vector space, which will talk the again space of vectors. As you know, in our 11-12 concept, vector means it has direction as well as magnitude, that is scalar quantity as a magnitude and direction I am talking about the vector quantity, please. So, it is associated with the two numbers, one set of vectors and it is set of scalar type of things. Now, basically we want to generalize this concept for the generalized system Ax equal to y, where A is a m cross n matrix over a field say capital F, and y is basically again m cross 1 column matrix, please, or column vector, please, like what we have written here. So, let us define vector spaces. The first question will be, what is vector spaces? This is a question, please. I can write like this: a vector space consists of two sets. The one set of objects or vectors, which can be denoted as capital V, and a field of scalar. Another one is a field of scalar. Here I am denoting as a standard notation F, along with two binary operations. One is called vector additions, I am denoting this as plus, and other one is scalar multiplication. I am denoting as star, such that with respect to vector addition, capital V is an abelian group, that is it satisfied closure property. For any u and v belongs to capital V, u plus v also belongs to capital V, and sum of two vector is again a vector place. Second is associative property. For any u v w belongs to capital V, u plus v plus w equal to u plus v plus w. Third one, existence of additive identity, that is we can say zero element. I mean there exists an element E belongs to capital V such that for any u belongs to capital V, u plus E equal to E plus u equal to u. E is called zero element. Existence of additive inverse. For any u belongs to capital V, there exists small v belongs to capital V such that u plus v equal to v plus u equal to that zero element E. Commutative property. Property also holds good. That is, for any u and v belongs to capital V, u plus v equal to v plus u. So, with these 5 axioms, V has to be an abelian group with respect to vector addition, and then with respect to scalar multiplication, it has to satisfy again 5 more axioms. The first is, scalar multiplication means it deals with the scalar quantity from the field and vector quantity from the capital V. This is a basically association with these two set of element plates. So, first is closure property. I mean to say, for any C belongs to capital F and U belongs to capital V, C star U also belongs to capital V. That is closure property holds good. Second one, for any C1 and C2 belongs to capital F and U belongs to capital V, C1 plus C2 star U equal to C1 star U plus C2 star U. So, note that this plus is basically binary operation in field place, but this plus, what I am saying here is the vector addition place. See, and 1 belongs to F, and for any u belongs to capital V, 1 star u equal to u star 1 equal to u. Fourth one, for any C belongs to capital F and u as well as V belongs to capital V, C star u plus V equal to C star u plus C star V. That is distributive property over the addition also holds good. And the last one is a fifth one, for any C1 and C2 belongs to capital F and U belongs to capital V, C1 into C2 star U equal to C1 star C2 star U. So, with respect to scalar multiplication, it satisfied all these 5 axioms, and with respect to vector addition, it is an abelian group. So, then only we can say it is a vector space. And the definition of a vector space, definition of a vector space I can say like this: a non-empty set V is said to be a vector space over a field capital F. I will have to say that V equipped with 2 binary operations vector addition and scalar multiplication. Okay. Equipped with 2 binary operation is said to be vector space over the field F, provided V is an abelian group with respect to vector addition and with respect to scalar multiplication it satisfies following 5 axioms. That is already have discussed. One is closure property for C belongs to capital F, U belongs to the capital V, C star U belongs to capital V. Associative property type for any C1, C2 belongs to capital F and U belongs to capital V, C1 into C2 star U equal to C1 star C2 star U. It is not exactly associated, but it is type associative. Third, there exists one belongs to capital F such that for any U belongs to capital V, 1 star U equal to U and equal to also U star 1. Fourth, for C1, C2 belongs to capital F and U belongs to capital V, C1 plus C2 star U equal to C1 star U plus C2 star U. and for distributive property over the addition also holds good for any C belongs to capital F and U V belongs to capital V, C star U plus V equal to C star U plus C star V. Okay, so this is the definition of the vector space. Now, let me consider some examples. Let V be the set of all n tuple over capital F, that is V equal to collection of all the points like x1, x2, xn such that xi belongs to capital F, this one. This can be written also, it is like in a standard notation, that is Fn. Okay. So, V is the collection of all the n tuples like this over the F. F is any field, it may be real number, it may be complex number. Consider two binary operations. One is vector addition and two is scalar multiplication as below. For any your U and V belongs to capital V, U plus V which is equal to U1, U2, Un plus V1, V2, Vn which is equal to, I am writing U1 plus V1, U2 plus V2 and like Un plus Vn, and this is my vector addition 1, and scalar multiplication is like this for any C belongs to capital F, C star U equal to simply C U1, C U2 and C Un. So, this is my scalar multiplication over this given set capital V. Claim V is a vector space. Now, to prove that one, I have to show that V satisfied all the axioms in the definition of the vector space, please. I mean to say V is an abelian group with respect to binary operation 1 and with respect to scalar multiplication 2, it satisfied all the 5 axioms. So, first let us quickly check that whether V satisfied all the axioms of the abelian group or not. First, closure property. Closure property means what I have to check? I have to check, suppose U and V, there are two n tuples I have considered over the capital F. I have to show that the sum of two n tuple is again an n tuple over the same. So, I can say that the way the vector addition is defined and is defined certainly for any U and V belongs to V, U plus V belongs to capital V. So, closure property holds good. What can you say about the associated property? Let me quickly check it that once. For any U V W belongs to capital V, we have U plus V plus W. I can write down this is equal to, I have to show that U plus V bracket over plus W equal to U plus bracket start V plus W. That is what I have to prove it. This is equal to, from the definition 1, I see that this is equal to U1 plus V1 comma U2 plus V2, then Un plus Vn. The first inside the bracket part is like this, then plus again your W1 comma Wn. So, this is again finally going to be again U1 plus V1 plus W1 comma it will be Un plus Vn plus Wn. So, I am getting like this. Now, this number is over the field capital F, which is also satisfied the associated property. So, therefore, I can write down this one as a U plus V plus W equal to H. I can write down again U1 plus V1 plus W1, I can write like this, then U2 plus V2 plus W2 and so on, Un plus Vn plus Wn like this. So, this is again nothing according to definition 1 of the vector addition, we have this is equal to U plus V plus W, please. So, associative property holds good. What will be our existence of 0 element? Third one, see for 0 element I will say that consider E equal to suppose E1, E2 and En be a 0 element, 0 element of capital V. Then according to definition of the vector space, we have for any U belongs to capital V, U plus E equal to U. So, this implies I will have U1 plus E1, U2 plus E2 and Un plus En equal to U1 comma U2 comma Un. Since these two entuples are equal, therefore, comparing the each component they have to also equal. So, considering this implies that U1 plus E1 equal to U1, this implies that E1 equal to 0. It is a number from the field capital F. So, E1 equal to 0. So, similarly E2 equal to 0, E3 equal to 0 and En equal to 0. So, this implies that E equal to 0 comma 0 comma and 0 please. So, this is the 0 element Fn please, I mean V equal to Fn please. What can you say about the additive inverse? For any U belongs to capital V, U is equal to basically say U1, U2 and Un. Then let V equal to V1, V2 and Vn, which is again an entuple which is belongs to capital V. Suppose if it is a inverse, additive inverse of U such that U plus V equal to E. So, this implies that I will have U1 plus V1 equal to 0, U2 plus V2 equal to 0 and so on. So, Un plus Vn equal to 0. This implies that my V is nothing minus, I mean V1 equal to minus U1. So, minus U1 minus U2 and minus un. This is the inverse of this element u, please. Next is a commutative property. We have to check whether commutative property holds good or not. For any u and v belongs to Fn, we have u plus v is equal to as a u1 plus v1 comma u2 plus v2 and then un plus vn. So, each component are basically from the field. So, which is basically also satisfied commutative property. So, this can be written as similarly as v1 plus u1 and vn plus un. So, this means that this is equal to v plus u. So, it satisfied also commutative property. Similarly, we can check, one can check Fn satisfies all other axioms with respect to scalar multiplication also. Multiplication. So, V equal to Fn is a vector space. Now, if I consider n equal to 1, then we have V equal to basically F. So, here set of a vector is capital F and set of scalar is also capital F. So, you can say that we can prove in the same way that F over F will be also a vector space. Let me consider the F equal to say complex number. That is my set of vector is a complex number and the set of scalar that is filled as a real number. Now, question is whether set of complex number over set of real number will it be a vector space? Answer is yes. We can quickly check it satisfied all the axioms of the definition of the vector space. But if I consider set of vectors as a real number and set of scalar as a complex number and operation is vector addition scalar multiplication, you can see that it will be not a vector space because it will not close with respect to scalar multiplication, please. You can think about it, you can take it as a home assignment also. So, now let me take another examples. Let capital S be a subset of the real number R, subset of real number R, please. Let V be the collection of all functions from S into R. Consider vector addition and scalar multiplication as below. Vector addition like this for any F1 and F2 belongs to capital V, F1 plus F2 of S, because F1 and F2 is the function from capital S to R. So, F1 plus F2 of S is equal to F1 of S plus F2 of S. So, this is my vector additions and scalar multiplications I can define like any scalar C belongs to your field say R here, C star and F, this is equal to C star F of S please. Actually this is not star, it is basically C into this one please. This is normal product please, because Fs is also belongs to R and C also belongs to R. So, it is normal multiplication this one please. So, this is my scalar multiplication. Now, vector addition and scalar multiplication we can check this set of all this function is also vector space please. I mean we can check, one can check, can easily show V is a vector space. I mean first we have to show the it satisfied that V is a basically abelian group with respect to vector addition, and with respect to scalar multiplication it satisfied again 5 more axioms. See, if I take f1 and f2 to any functions from V, f1 plus f2 of S is equal to f1s plus f2s. This also belongs to the, because each of them belongs to real number. I mean f1 of S belongs to real number, f2 of S also belongs to real number. So, f1s plus f2s also belongs to real number. So, this implies f1 plus f2 which is defined from set capital S to R is again a function. Therefore, it is a closed. Similarly, you can check it also satisfied associative property. I mean, so closure property we can immediately check like this. Associative property, how to check? Associative property you can check like this thing. For f1, f2, f3 belong to this your capital V, one can say that f1 plus f2, f1 plus f2 of f3, this of S, this is equal to, I can write down f1 plus f2 of S plus f3 of S, and this is equal to again f1 of S plus f2 of S plus f3 of S. So, this nothing, because all are basically over the real lines. So, f1 plus f1 of S plus I can write down f2 plus f3 of S please, this one. So, this implies what? This implies f1 plus f2 plus f3 equal to f1 plus f2 plus f3. So, associative property also holds good. What about the 0 element? The 0 function itself is 0 elements. What about the inverse? If f1 is there, I can say minus f1 also there. So, f1 plus minus f1 is 0 function this, and f1 since it is defined over the basically real line and which is basically abelian. So, therefore, a commutative property also holds good for this set capital V please. With respect to scalar multiplication, see for any C1 given definition, it is again clear that C times F of S is basically C times F is again a function from capital S to R. So, closure property holds good with respect to multiplications. And we can also check for 4 more axioms of the with respect to scalar multiplications, which also holds good for the given set of vectors over the given set of scalar please. So, we will see that this is also vector space please. It also satisfied all other axioms of vector space. So, it is a vector space. Now, next examples we can consider, let V be the collection of all polynomial functions over R. Consider vector addition as for P and Q belongs to V. Okay, for sake of simplicity, let me consider collection of all polynomial function of degree less than or equal to n, please. This one suppose, but over R, please. Now, P is equal to something like P naught plus P1 x plus P2 x square plus I can say Pn x to the power n, and Q equal to, let me consider Q naught plus Q1 x plus say Qn x to the power n. So, let me define vector addition P plus Q as defining as a P naught plus Q naught, then plus P1 plus Q1 x plus P2 plus Q2 x square plus dot dot plus Pn plus Qn x to the power n. So, this is my vector addition, please. And scalar multiplication as for C belongs to my R, C times P equal to, I am defining, this is star, please, C P naught plus C P1 x plus like C P n, please, x to the power n. So, this is my scalar multiplication. Again one can check with respect to this vector addition and scalar multiplication, this set of collection of all the polynomial of degree less than or equal to n is again a vector space, please. So, I hope you have understood the definitions of the what is vector space, and by this couple of examples I will definitely continue with that. So, we have defined what is our vector space, we have seen different vector spaces through these different examples. So, we will continue in our next class the further development in these directions. Thank you.